So today we're going to start doing some real stuff with probability. We'll do a little bit of the general theory, and then I will end, hopefully, with playing roulette with you and teaching you why you should not play roulette with me. Okay? As a rule of thumb, you should always be suspicious when a mathematician says, hey, you want to play this really cool game. Okay? We're going to start off with the expected counts method. And what we're doing is we're trying to find out what's a good way to define probabilities of events. Okay, so let's say we have a fair coin, toss toss twice. And we want to calculate the probability of events. So what are the possible events? Heads or tails. So I toss it twice. What are my possible outcomes? Yes? Okay, so you're correct, but is that the order you want to write them? I would probably not. I would probably write head, head, and then let's say I'll keep the head fixed and I'll change the second one and go head, tail. Now I'll change the first one and then tail, tail. So you want to make sure that you don't forget any possibilities. And so what I'm doing here is I'm going first all the ones that have exactly 2 heads, all the ones that have exactly 1 head, all the ones that have no heads. And it's just very important not to miss things. Now, this is not that hard of a problem to figure out what are the probabilities of each of these events. If it's a fair coin, what should all these probabilities be? 25% or 1/4. All right, so now let's change it. So instead of being a fair coin, let's say the probability of a head is 7/10. And so the probability of a tail would be 3/10. So I think it's pretty clear what you would expect. So what should be the probability of head, head? 49 out of 100, 0.7 squared, all the way down to 0.3 squared here. And then each of these should be 0.7 times 0.3. So I realize that this is a very basic problem and this is a little bit of an overkill, but it's a way to just highlight the method. So the way the expected counts method works is you just imagine a huge number of events, and for each one you start with a huge number of initial conditions and just see how it flows down. I want a nice round number, and I want the number so that when I do my first case, 70% of the time I'm going to get a head, 30% of the time I'm going to get a tail. So it seems reasonable I might want to start with a number that's a multiple of 10. I'm going to do this twice, so maybe I want a number that's a multiple of 100. I'm going to choose a number that's a multiple of 1,000 just to give myself a little bit of protection. I was at the Museum of Science. I didn't come back till about 2 a.m. last night. I'm tired right now. I don't trust my algebra. So give myself a little bit of protection. So we start off with 100 situations. And now we do the first toss. How many times will we end up with a head? And how many times would we end up with a tail? Yeah, so we should have 700 heads here, and then 300 here. And then we do it again. And now when we do it again, how many heads should we have here? Yep, which is 490. And then over here, I should have 30% of 700, which should be 210. And then here I would have head and tail. Notice I'm always having my heads on the left. I'm always having my tails on the right, trying to minimize chances of errors. This should then be 70% of 300. So 210 times I'll be down here, and 490 times I'll be down here. Oh, no, something's wrong. No. Told you I don't trust my algebra. 90 times? Okay. This should all add up to 1,000, because that's how many things we started with, and we just saw how we flew to the different events. So this is the expected counts method. I really don't need it for a problem like this. I can pretty much figure out what's the probability of a head-tail. But it's just nice to have a formal procedure to attack problems like this and to find the probabilities of the relative events. Now notice that this event is head-head, this event is head-tail, this event is tail-head. If I care about just the event that I have one head and one tail, I would combine these two. And that would become 420. This is the one head, one tail event. And so you can combine a bunch of things. Okay, I don't want to say too much about the expected count method. The example is in the book. What I want to do now is I want to go to Kolmogorov's Axioms of Probability. All right. Now, will we be able to prove an axiom? No. The name itself is basically an indication. This is something you're assuming. Can mathematicians assume anything? Can we make anything an axiom? Yes, it's wonderful, right? Now, if one of your axioms is the statement A and another of your axioms is the statement not A, this would be a bad choice of axioms. This would be a contradictory set of axioms. And in fact, the laws of logical inference would now allow you to do anything you want. So normally we require that our axioms are consistent. You should not be able to prove both a statement and its negation from your set of axioms. It is not always easy to prove that your axioms are consistent. Sometimes what you can only do is prove relative consistency. If this set of axioms is consistent, if I add this additional axiom, it doesn't make it inconsistent. It may not have been consistent to start with, but it's not going to be harmful to add this one. So our axioms, do they just come to us out of the void? Where do mathematicians get their axioms from? Yes? Experience. So while a pure mathematician can study anything in the world, or possible worlds, how we actually do mathematics is profoundly influenced by the fact that we live in this world. And that is going to affect what we choose as our axioms and what we think is reasonable. We could try to be like a rebellious teenager and rebel against the world and put in some kind of contradictory or opposite axiom to what we're seeing. But that's still being derived from our experiences. So our experiences will profoundly affect our mathematics. It's just worthwhile to be aware of this. All right, so what we're going to do for Kolmogorov is we have a triple. Omega is our outcome space. Sigma is the set of elements, or the set of subsets of omega that we can assign probabilities to. And PR is our probability function that will assign probabilities. And we're going to assume the following things. The first is, if A is in our sigma algebra, that's a helpless sigma, then the probability of A is in the interval 0, 1. Okay, bless you. Does that, and it exists. All right. So this is essentially just making explicit some of the rules of the game. We're saying that we should be able to assign probabilities to anything in the sigma algebra. We can assign a probability, and the possible value we assign is between 0 and 1. No matter how likely something is, it does not exceed 100% chance. Okay. Does this seem that bad? Okay. Next one. The probability of the empty set is 0, and the probability of omega is 1. So think of it as we are assigning probability to the space omega. The whole space is given probability 1. And that probability is going into some of the elements in some way. And so if we don't have any elements, no probability was assigned to that. All the probability is given somehow to the elements of omega. Does this seem reasonable? All right, and then the last one is, if the set AI is at most countable, then the probability of the union of the AIs is the sum of the probability of the AIs if disjoint. So what this is saying is if we have a collection of disjoint sets, and it's an at most countable collection, then the probability of the disjoint union is the sum of the probabilities. We saw last time that if it was not a countable union, there were potential issues. And so that lecture can now be forgotten. It served its purpose. Okay? We will only be working with countable unions. And the last axiom is that if we have a countable union, then the probability of a disjoint union is the sum of the probabilities. This is wonderful. This allows us to break complicated events into a bunch of simpler events. It depends a little bit on the problem, but which would you rather do? Infinitely many simple things or one very hard thing? And it depends how you piece them together, but frequently it's a really good trade to break things up into cases. When you break things up into cases, you have more things at your disposal. This is typically a good way to progress. Okay, so now there's a couple of consequences from stuff like this. And what I want to do is, before I go into those consequences, I want to look at the probability of a specific item. And this will build a little bit on what we did last time. So let's consider two events A and B. And I want to calculate the probability of A union B. So I want the probability of A union B. And maybe here's my set A, here's my set B, and here is my entire space omega. So A and B live inside omega. Here's my event A, I've assigned some probability to A. Here's my event B, I've assigned some probability to B. I want to figure out what is the probability of A union B. So what do you think it should be a function of? What are the possibilities? What are the possible building blocks? Yes? Good. It seems to make sense that whatever formula I have is going to somehow involve these quantities. Right? You know, if you look at it, I've got A, I've got B. This part over here is A intersect B. Now, there is a way to quickly find this out. We could write A union B as a disjoint union. Right? We could write A union B is a union of three sets. So one set is clearly A intersect B. What's another set? Yes?
A and not B?
A intersect B complement, or not B. So A intersect B complement is the stuff in here that's not. And the last one is A complement intersect B. So that's a disjoint union. So we could now use property 3 and get the probability of A union B is the probability of A intersect B plus the probability of A intersect B complement plus the probability of A complement intersect B. Okay? So then we would have to figure out what's the probability of A intersect B complement. Yes?
Probability of A minus probability of A intersect B.
Okay, so we're going to do this very carefully. So A is equal to A intersect B complement union A intersect B. I can't subtract. I don't know how to do that yet. But I can say, since A is equal to this disjoint union, I can then write the are people able to see if I write down here, or are people in the back not able to see? I'm not hearing anybody saying no from the back, so I'll keep writing. So the probability of A is the probability of A intersect B complement plus the probability of A intersect B. So now we get the probability of A intersect B complement is the probability of A minus the probability of A intersect B. And so we can fill in for that. We can similarly fill in for this. And when the dust settles, we will get a formula. At the end of the day, this gives us the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. So when the dust settles, that's what we get for our formula. Okay, and the way we did it was we did it very slowly. We wrote our event A union B as a disjoint union. And then to figure out what's the probability of this event, A intersect B complement, we noticed that this event A intersect B complement union A intersect B is just our event A. And so we keep reducing everything in terms of things we know, and at the end of the day, we get this wonderful formula. The probability of the union is the sum of the probabilities minus this double counting. And if you look at what's going on, well, yeah, that makes sense. Here's A, here's B. Oh, well, if I just add their probabilities, I've counted this region twice. So if this region has any probability, I've overcounted it. I've got to subtract it once. So this is a very reasonable formula. What I want to talk for a few minutes is how we could have sniffed this formula out by doing a special case analysis. So do we all agree that it should be a function of the probability of A, probability of B, probability of A intersect B? There's really no other sets in play. So let's assume that there's some kind of relationship between them. What's the simplest possible relationship? Simplest possible relationship. Yes?
They're all the same.
Well, I mean, I want a formula involving these three. What's the simplest way to combine them?
Oh, adding them?
Adding them. Or maybe adding them with some kind of weights. So we could assume some kind of linear model. So let's assume we have a linear model. So assume the probability of A union B is C1 probability of A plus C2 probability of B plus C3 probability of A intersect B. We don't need to do this. We already know the formula for the probability of A union B. I deliberately erased it so that you would not be looking at it right now, although you have your notes in front of you if you're doing a good job, so it's limited success here. But let's try to think of some special cases. So can anybody think of good choices for A or B? Yes?
Omega in the empty set.
Okay, so one possibility is always the omega in the empty set. Well, in fact, if we just take B to be the empty set, then we get the probability of A is C1 probability of A plus 0 plus 0. So you want to get into the habit of, if you have some kind of relationship that you're trying to sniff out, what are good test cases to do? What are good sets to play with? It was said, take A equals the full set. If we do that right now, we see that the probability of A is not 0. What's the only thing C1 could be? Forces C1 to be 1. This doesn't prove that this formula holds. It just says if there's going to be a formula like this, the only way it can happen is if C1 equals 1. So again, the purpose of what we're doing now is not just to prove this formula. We've already proved it. This is to try to give you an introduction to theoretical mathematics. So how would you sniff out a formula? How would you try to figure out what to prove? How many of you have proved things by mathematical induction? Is it easier or harder if I give you the formula? It's much easier. If I say, prove by mathematical induction that the sum of the first k powers equals the following. Oh, okay. not so bad. If I don't give you the formula and you have to sniff out that formula, it's a lot more work. So the goal is, how do you sniff these things out? So we just showed by choosing B to be the empty set that the only possibility is C1 equals 1. Can somebody give me another good choice?
A equals
Yeah, try A equals the empty set. You know, why should B have all the fun of being empty? Now you would get the probability of B is 0 plus C2 probability of B plus 0. And now you get that C2 equals 1. Okay. We need some more choices. We don't know anything about C3 yet. What should we choose for C3? Yes.
Probability of A and, well, A and B are both omega.
Okay. I think you could actually weaken it to just A equals B, and then probably later we'll correct in a moment to omega. We can take them to be omega. And then in that case, we get the probability of omega. We already know C1 is 1, is the probability of omega plus the probability of omega plus C3 probability of omega. What's the only possibility for C3? Negative 1. And that's the proof. That doesn't prove, again, that the formula is correct. It just shows that if there's any formula that linearly depends on the three quantities that have to be at play, the only one that will work is 1, 1, negative 1. And it's really nice to have that. Now when you're trying to prove things, you have an idea of how to do the analysis. How should I break things up now so I get probability of A plus probability of B minus probability of A intersects B? Oh, okay, I'm double counting. And so, again, this is overkill for this problem. I understand this is overkill for this problem, but it's to just get you thinking about problems in this way for later. There will be times in the semester where it will not be clear what to do. I shouldn't smile so much. Where it will not be clear what to do. Okay. Any questions? Okay. So we want to start moving on to some consequences of Kolmogorov's laws of probability. So the first is the law of total probability. Probability of A plus the probability of A complement equals 1. So essentially what this is saying is the probability that either A happens or A doesn't happen is 1. So we should be able to deduce this from Kolmogorov's axioms. All right, well, we have a disjoint union. The probability of the union is the sum of the probabilities. And so what we can do for the proof is we can write omega is A union not A. And now we would just have the probability of omega is the probability of A plus the probability of A complement. And by Kolmogorov's, bless you, second axiom, this is equal to 1. And that would finish the proof. It's sometimes interesting to see how much do you need to assume? And what can you get from those consequences? Has anyone here taken abstract algebra? All right, because you've taken group theory. All right, so when you do the axioms of group theory, you often assume that there's an identity element, that every element has an inverse. And you normally talk about having a two-sided identity and a two-sided inverse. You actually don't need to assume that. That's overkill. If it's just one-sided, that's enough. Most people don't bother with this weaker assumption. But it's sometimes interesting to see how far can you push things and still get the result. Okay, so that's our first consequence of Kolmogorov. We've already used this in this semester when we were doing the birthday problem. To calculate the probability that something happens is the same as finding the probability it doesn't happen and then subtract that from 1. So frequently it's easier to calculate one event than another. If we're doing games with cards, and I want to calculate what's the probability you're dealt 6 cards and you have at least 1 king. I could have 1 king or 2 kings or 3 kings or 4 kings. Or I could just say, let's calculate the probability I have no kings and subtract that from 1. So frequently, depending on where you are, it's often easier to calculate the probability of the complementary event. Okay. The next one was the probability of A union B is probability of A plus probability minus probability A intersect B. We've just done that. So I'll just write this here as 2. Probability of A union B is probability of A plus probability of B minus probability of A intersect B. All right, we've done that. The next one is the inclusion one. Yes. If A is contained in B, then the probability of A is less than equal to the probability of B. This should be screaming at you, of course. We've done it right? Yes. B is larger than A. It has at least as many things. I can't be assigning negative probabilities. The probability that B happens can't be less than the probability that A happens. But we want to prove this rigorously from our axioms. We don't want to have to use this as another axiom. So the proof is we want to somehow write B as a disjoint union, because we know how to do probabilities of disjoint unions. Well, can anybody tell me one of the ingredients in the disjoint union? Yes? A. Because we're trying to show B is A plus something else. So what do I need to add to A? Yes?
Union of A complement and B.
Yes. So, wait, the union of A complement and B?
Or like everything in B that's not in
Good. So it's B intersect A complement. So it's everything in B that's not in A. And now we have the probability of B is the probability of A plus the probability of B intersect A complement. And this is greater than or equal to 0, and that finishes the proof. So we don't need to have a separate axiom that subsets have smaller or equal probability than the superset. It follows from our axioms. And then there's one more. I'm not even sure it's worth writing down, but I did last year. So if we have AI is contained in B, at most countable and disjoint, then the sum of the probabilities of AI is less than or equal to the probability of B. So I'm not going to go through and write down the proof of this, but each AI is at most B. The union is disjoint, so the union of everything is also less than B. So now from here I get the probability of the union is less than or equal to the probability of B, and then I use Kolmogorov's third axiom and say that the probability of the union is the sum of the probabilities because it's disjoint. So this just helps us get some sense of how to attack a bunch of problems. Okay. Any questions on what we've done up till now? So now we have enough of the tools of probability to start attacking a huge number of problems. Okay? So chapter 3 starts going through, I think, card counting problems, problems in blackjack. Well, maybe not blackjack. I think poker's there, bridge is there, solitaire is there. There's a lot of different things to do. A lot of them are very similar. I will do a subset of things. Okay. What I want to do for the rest of the time today is talk about roulette and the connections between roulette and the Fibonacci numbers. Okay? It turns out the same mathematics behind the Fibonacci numbers is the mathematics you need behind roulette. How many of you have ever played roulette before? Okay. Do you know how? Okay. So, anybody know how roulette works in a casino?
Like you bet on either a number, like a color, depending on how much money you
Right.
bet.
So we'll see if this works.
Yeah.
All right. So you can bet on numbers. You can bet on colors. And the way the wheel works,
Spin the wheel.
you can spin the wheel. There's a little metal ball. Sometimes there's a magnet under the table to make sure it lands where the deal. Oh, sorry. So you have reds, you have blacks, and you also have the greens. You have 0 and 00. The purpose of this is to give the house a little bit of an edge. So let's say you bet $1 on red. And if red comes up, Vegas gives you $1. If it doesn't come up red, you give Vegas $1. If there were no greens, then it would be a fair bet. and you'd be indifferent to either side. There are 2 greens, however, so the probability red comes up is a little bit less than 50%. Does that mean it's good to be the gambler or good to be the casino? It's good to be the casino. They've given themselves a little bit of an edge. Do you think this is fair?
It's a casino game, so I'm going to say no.
You can also bet on 0 or double 0.
You can, but the odds are set up so that it's a little bit against you. Not a huge amount. You know, it's close to 50-50. Yes?
I think it is fair because, like, if it was 50-50, they're covering all the overhead, but as well.
That's a really nice way of looking at it, you know. So then the question is, how much do they need to cover that overhead? The expression I've heard is, somebody has to pay for Mr. and Mrs. Smith's suits. And so, you know, what profit margin do they have? For the one-eyed bandits, the slot machines, they're required by law to pay out a certain amount of money. But I think they're only required to pay out something like 80% of what they bring in. So it's, you know, wonderful, wonderful way. So because Vegas has a slight advantage, I think it's only fair that I give you guys a slight advantage. So I'm going to show you how to use some mathematics to attack roulette. If we do not finish this in time, I will tell you what to watch online for the rest of it. I just want to make sure everybody understands I am not advocating you go to Vegas and use this. However, if you do go to Vegas, use this and make a lot of money, I want you to remember where you learned it. Okay? So how many of you have ever heard of double plus 1? Okay, a few people. So when I was very young, my father actually wrote a computer program to do this. And in fact, when I was at the Museum of Science last night, I actually wrote a program live. I coded in front of people to show that, you know, my calculations were correct. And we just ran it in real time. So here's the way it works. You start off and you bet $1 on red. Okay, so you bet $1 on red, and sadly it comes up black, so you lose. You're down $1. You double your wager and you bet $2 on red. You lose again, not today. How much are you down? $3. You double your wager again, and now you bet $4. You lose again, it's not today. How much are you down? 7. You double your wager again, you now bet 8. So I have a 5, I have a 2, and I have a 1. So now we bet $8, and you win. How much are you net? Plus 1. So all of this, all that it does at the end of the day is you're only up $1. Now, of course, if $1 is not enough, you could, of course, bet, you know, $1,000 initially rather than $1. But now what you do is you do the Shampoo Method. How many of you have ever read the instructions on shampoo? Yes, shampoo has instructions. Yes. What are you told to do in shampoo? Lather, rinse, repeat. So once you've won $1, you just do this again and you win another $1. Then you do it again and you win another $1. This sounds good, right? Eventually a red's going to come up. Even if the house has a little bit of an advantage in that they have those greens, eventually I'm not going to get infinitely many blacks, right? Eventually a red will come up, I'll win $1. I then do this again. So please don't take this the wrong way. I love my job. I love teaching at Williams. I am enjoying getting to know you. But if this method would work, I'd be in Vegas. Or I would be dressed very differently, and I would not be teaching 9 a.m. classes. There would be the Miller Chair of Mathematics that teaches at a much more... Oh, wait, this is 10 o'clock. I wouldn't even be teaching at 10. Right? There's got to be a mistake in this. What's wrong? Yes?
Don't they have like minimum?
Okay, no, I don't want that one. I want something else that's wrong. Yes?
You might run out of money.
So you might run out of money. You also might not have the intestinal fortitude, you know, when you've just lost $1 million wager to put down $2 million. So what I'm going to do is I'm going to assume the existence of the eccentric rich aunt or uncle. Okay? How many of you are taking an econ class? You wouldn't laugh at econ when they give you their assumptions. You know, you should show the same respect in a math class. Okay? So the eccentric rich aunt or uncle will stake you however much you need. They won't give you $1 directly. If you say, could you give me $1? No. I need $2 billion. Sure. Okay. There's a reason they're eccentric. Okay. So you never have to worry about having the cash reserves. You can always place the wager. Okay. Now we'll go to the other issue. Yes.
Yeah. Houses have like min and max and bets.
Yes.
So actually not to be able to jump up.
Let's say the minimum bet is $1, and let's say the maximum bet is, say, $20. So let's say you lose, you're down $1. Then you lose again, down another $2. Lose again, down $4. Lose again, down $8. Lose again, down $16. And now you have to place a $32 wager, but the most you can bet is $20. So what happens is when you lose big. And when you win small. So the question is, how likely is it to get, say, 5 consecutive blacks and go bankrupt? If it's a very low probability of this happening, then you can use this method and make $1 with reasonable comfort and repeat it a lot of times and make a small amount of money with reasonable comfort. If, however, there's a large probability that you will get 5 blacks quickly, then this strategy is disastrous. Trust me, they have done the calculation as to where to set min and max. It is not guesswork. They make sure that there's a very good chance you will have the string of bad luck. The other thing which they do, which is really nice, is they do a lot of stuff with human psychology. So a lot of morons can be classified into 2 different groups. They now display the last couple of results of a roulette wheel, and you have the morons who go, it's been black 5 times in a row. Black is doing well. Got to bet on black. What's the other type of moron?
It's been black 5 times in a row. It's time for a red.
It's time for red. Red is due. And they really don't care which type of moron you are. They do not discriminate against morons. They just take their money. And you can just keep putting your money down and they will happily take it. And you might win as an individual, but if enough people are doing this. So we want to calculate what is the probability of 5 consecutive blacks in n spins. Hopefully this now seems like a question that belongs in a probability class. Okay? I hope none of you will be going to Vegas and doing this, but the mathematics we're doing here applies to a bunch of other things in the real world. Okay? So let's let Pn be this probability. Let's see, do I want to do a Pn or do I want to do a Qn? I'll have it as, I think I want it as Qn is probability of 5 consecutive blacks in n spins. And then Pn will be 1 minus Qn, which is the probability not 5 consecutive blacks in n spins. Okay. What relation do we have between Pn and Qn? Yes?
I have a question.
Sure.
We're betting on red and we're calculating the probability we're going bankrupt.
Well, right now, yes. I mean, I'm calculating the probability that we have 5 consecutive blacks, and so if we're betting on red, this would cause us to go bankrupt. And I'm just curious as to how likely is this if we say spin n times. So if n is 100, how likely is it that we get 5 consecutive blacks in 100 spins? Is this a 5% likelihood, a 20% likelihood, a 1/10, a 90%? How bad is it? So what relation do we have between Pn and Qn? I've kind of almost written this already on the board. Pn plus Qn equals what? And in fact, that's why I just even wrote 1 minus Qn over here. I didn't even bother going through things. This is the law of total probability. Is it easy to calculate the probability that we have 5 consecutive blacks or that we don't have 5 consecutive blacks? It turns out it's easy to calculate the probability we do not have 5 consecutive blacks. All right. And so what I'm going to do now is I'm going to show you how you do the calculation. So I'm going to start off with Qn. And I have 2 possibilities. I get a black and I get a red. And what's the probability of each one of these? Yes?
A little less than 50.
So technically red is a little bit less than 50 in the casino. So if you wanted to, we could put it's 19 over 38. Let's just do the simple version with it 1/2. You can change it. I will give ourselves a little bit of an edge. So now here's my question. What is the probability that I do not have 5 consecutive blacks and n spins, given that my first spin is red? What is that equal to? I want, yes? No. I mean, I still have a lot more spins. I could still get 5 consecutive blacks somewhere. Qn is spinning n times. And now my first spin is not a black, so it should hopefully be a little bit different than Qn. I now have n minus 1 spins to do. My first spin was a red. What's the probability I don't have 5 consecutive blacks? Q of n minus 1. Right? Oh, I'm sorry, we're doing Pn. So, I'm sorry, these letters are P, not Q, sorry. We're doing the probability we don't have 5 consecutive blacks. Sorry. Right? Our first spin was a red. We have n minus 1 more spins to do. All right? This one was the black. So now let's split. We have black, red. Each one of these happens half the time. I start off black, red. What's the probability I don't have 5 consecutive blacks in n spins, given that I start off black, red? Pn minus 2. And I do this again. Black, red, Pn minus 3. Black, red, Pn minus 4. Crap, I'm running out of room. Black, red, Pn minus 5. I've run out of room on the board. All right, should we just cancel class and go home? No, I don't want you to be left thinking that this method could work. Do I need the board to go further? So what is the probability we do not have 5 consecutive blacks in a row, given that we start off with 5 consecutive blacks? 0. That's why I'm not that worried that we've run out of board space. Right? That's why it's much easier to calculate Pn than Qn, because now this branch dies, the tree is now finite. The probability over here is 1/2, 1/4, 1/8, 1/16, 1/32. And we get the following beautiful recurrence relation. We get Pn is 1/2 Pn minus 1 plus 1/4 Pn minus 2 plus 1/8 Pn minus 3 plus 1/16 Pn minus 4 plus 1/32 Pn minus 5. And we even know some initial conditions. What would P0 be? The probability that we do not have 5 consecutive blacks and 0 spins. 1. What's P1? What's P2? What's P3? P4? So we have the initial conditions, and then we can just march down. So this is a recurrence relation. And we can now just march down, march down, march down, march down. It turns out that there's a way to solve this recurrence relation and write down a closed form solution. And that allows us to jump forward. So if people are interested, let me know. I'm happy to talk more about that. We'll probably see a little bit of that later in the semester. This is very similar to the Fibonacci numbers. The Fibonacci numbers satisfy the recurrence fn plus 1 is fn plus fn minus 1. Each number is the sum of the two previous. The same mathematics that we use to understand the Fibonacci numbers, we can use to study problems like this. This is called a difference equation. It's a discrete version of a differential equation. This has depth 5. It has constant coefficients. These are very easy to solve. By solve, I mean we can write down a formula for it where it's going to involve roots of something like this. So let me just concentrate on the Fibonacci equation because that's a little bit easier to solve. If you do the calculation, if you were to spin 100 times, you have about an 80% chance of getting 5 consecutive reds. 5 consecutive blacks. So it's pretty high. And that was not using any of the greens. So let's solve the Fibonacci. So we have fn plus 1 is fn plus fn minus 1. And we'll say f0 is 0, f1 is 1. That's a good way to define the Fibonacci's. So my favorite method of solving the Fibonacci equation is the method of divine inspiration. How many of you ever used the method of divine inspiration? It's really nice. You just go like this, and then you write down the answer because you're divinely inspired. A lot of times in mathematics, if you have a candidate for the answer, it doesn't matter how you found it. You just have to show it works. The problem is the method of divine inspiration is sometimes fickle. You do not know when it will strike. Frequently, it actually does not strike during exams. So you've got to be careful, but can you look at this and guess? So what I want to do is let's guess a little bit about the solution. Clearly, I know fn plus 1 should be less than or equal to twice fn. My sequence is growing. And what that means is if they had been exactly equal to 2, then I would have fn is basically like twice to the n. So maybe this suggests fn is slower or grows slower than 2 to the n. But I also know fn plus 1 is greater than or equal to 2 fn minus 1. Right? Because my sequence is growing. And so now I would get fn grows faster than basically like square root of 2 to the n. So this quick little analysis suggests that the Fibonacci numbers are growing exponentially fast. But it doesn't tell us what the correct answer is. So let's just call it R. So let's guess maybe the solution is just R to the n. Fun as a Bostonian to say this. Okay, so we plug this in, and what do we get when we plug this in? We would get R to the n plus 1 is R to the n plus R to the n minus 1. We pull out the R to the n minus 1. We get R squared minus R minus 1 equals 0. We get R equals 1 plus or minus the square root of 5 over 2 using our friend the quadratic formula. And what's nice about this is technically R could be 0. Well, if R is 0, then everything is 0. That satisfies it, yes, but it's a boring solution. If I have a solution, if I multiply a solution by 5, it's still a solution. Because this is a linear equation. And if I add 2 solutions, it's a solution. So you actually get the general solution is going to be some constant 1 plus root 5 over 2 to the n plus another constant 1 minus root 5 over 2 to the n. We're running out of time. This number is the more important one. This number is greater than 1 in absolute value. This number is less than 1 in absolute value. When n is very, very large, the nth Fibonacci number is essentially this. And in fact, the nth Fibonacci number is the closest integer to this. Okay? What you can now do is you can now try to figure out what are C1 and C2 by using the initial conditions. We know when we take n equals 0, we get 0. When we take n equals 1, we get 1. So after a little bit of algebra, you end up getting it's 1 over root 5 and then a minus 1 over root 5. And this is called Vinay's formula. If you take a class with me, you very quickly learn this is one of my favorite formulas in all of mathematics. It's a closed form solution for the Fibonacci numbers. It allows you to jump to the nth Fibonacci number without wading through things. It gives you an idea of how quickly they're growing. And it does not look like an integer. Everything cancels. It's a nice exercise. What can you replace the 2's and 5's by and still have an integer? Okay, so there's a lot more that we can do with difference equations, but this is at least our first real application of stuff we've done. We've already done enough to show you should not go to Vegas and use the double plus 1 strategy. So if any of you had plans for that, please change them. Okay?